last time, or in the previous video, we had this differential equation, and we solved it, and we got this general solution. There's one, I thought I was done, but there's one more thing I wanted to add, actually. So we imposed some specific initial conditions that made one of the constants end up being 0. And so it was pretty easy to interpret what we were looking at afterwards, because it was just one of these terms, and so it was a sinusoidal function times a time-varying amplitude. But what if your initial conditions are more complicated? So let's say, for example, you have these initial conditions. Same differential equation, but these initial conditions. X of 0 is 5, x prime of 0 is 1. In the previous video, we had 0 here rather than 5. Then use basically the same technique, solve for C1 and C2, and I got these numbers. Not really important what they are. And so the solution to this initial value problem, same differential equation from last time, and these new initial values, I got this general solution where I've put in my numbers that I solved for. C1 is this and C2 is that. And my question now is, what does this look like? So now it looks a lot more complicated, right? It doesn't look like it's just some sinusoidal function times a time-varying amplitude. So what does this look like? Well, one thing we can do is go and plot it in some program like Mathematica, and here's what it looks like. I mean, you can verify that this at least satisfies the initial conditions. It starts at 5, so the horizontal is time and vertical is x, and it starts here at 5, and the slope starts at 1. That's plausible. It looks like it starts sort of with going up like that. Apparently this is what happens when you start with a slope of 1. It comes back down quickly, and you've got the decaying amplitude, and it does look like it's oscillating. Maybe if I run time for longer, we can see if it continues to look that way. Like if I run it up to 15 or something. Yeah, it seems like it just keeps oscillating with the decaying amplitude. But can I analyze it in the same way that I analyzed that one in the previous video, where I said exactly what was the period, like what is the size of the, how long does it take for it to repeat? Not really repeat, because it doesn't repeat, but how about this? How far apart are the zeros? How long does it take for it to cross the axis twice? Yeah, so can we analyze it this way, considering that it looks so complicated like this? Well, we can definitely pull out the e to the minus t over 2, so that will help. So I can just pull this, I can overall pull this out, like this. Okay, sorry, then the 5 is on here. Yeah, so we can definitely do this. And now it looks like e to the minus t over 2 times what looks like a linear combination of a sine and a cosine, where the angular frequency is the same. So it's 5 of this cosine and 7 over root 3 of this sine. And the angular frequency is the same. So it is worth it to try to understand those kinds of functions and see what they look like. So what I mean is just this part that I circled here. We totally understand this. It's exponential decay. So this is being multiplied by some exponential decay. But what is this part? So one thing I can do actually is just try to plot that part by itself. So let me go ahead, instead of plotting the whole thing, I'll plot just that part. Okay, so this is the same plot I had before, except I removed this exponential decay term that's sitting in the front. So now there's no exponential decay, and it looks kind of big, so let me sorry, this is not fully on screen. There. Yeah, so that's what it looks like. So this is a 5 times a cosine plus 7 over root 3 times a sine, and the angular frequency is the same. And what you see, I mean, what does this look like to you? It's just a sinusoidal kind of function, right? It looks like a sine or a cosine, except with a certain amplitude and maybe phase shifted. So shift with the graph shifted horizontally to the left or right. what we would like to do is try to understand, if we write this as a sinusoidal function, then what is its frequency, or period, or angular frequency? And what is its amplitude? That would be nice. So like, this alone has amplitude 5. This alone has amplitude 7 over root 3. But what about this overall? How high is this? It looks like it's a little bit above 6. You know? So can we answer this kind of question? Actually, here's another interesting thing we can try. Let's plot C1 times sine, and then let me put 2t, plus C2 times the cosine of 2t. And I just randomly chose the angular frequency 2. But I just want to see what happens as I change these coefficients in front. What kind of different things can I get as I change these coefficients? It doesn't matter if what the angular frequency is for what I'm trying to show. I just want something simpler to type. Let's plot it from t equals 0 to t equals 10 or something. And of course, I'm not going to see anything because I need to say what are C1 and C2. So let's make it so that you can control what they are. Okay, so now I've got these bars that I can move around to manipulate things, and it looks like as I move the bar, the vertical axis scale changes. So let me fix the vertical axis scale to -5 to 5, say. Then watch what happens as I move the bar, as I move this C1 bar. So here they're both varying from -3 to 3. So here's C1 equals -3 and C2 equals -3. And as I move these bars, it's kind of interesting. The sinusoidal function shifts around to the left and right, and the amplitude changes, right? But it stays looking like a sinusoidal function. It's not something more complicated than just like a sine or a cosine, even though it's a combination of both. If I made the frequencies different, like if one was sine 2t and the other is cosine 3t, then things can get super weird, right? But that's not the situation that we will find ourselves in with the general solution in case 3 that we're looking at. Like, no matter what, I was going to end up with the same frequency here and here. So it's actually the simple situation where you just have a sinusoidal function. Okay, so question. Can we figure out, given something like this, or something like this, can we figure out what is the amplitude and what is the period? So this is my question. Given something like C1 cosine omega t plus C2 sine omega t, where it's the same omega here and here, same angular frequency, what is the amplitude and what is the period, or frequency or angular frequency? So we know that this, which looks complicated, is just some sinusoidal function. So what kind of function is it? Okay, well, if it starts out looking like this, and we think it's a sinusoidal function, then maybe we can write it in this form, that it's just a cosine, or just a sine, so I'm just going to pick one. I choose cosine, with some amplitude in front, let's call it A, and some frequency, let's call it beta, and some shift, some amount of shift, let's call it delta. So let's guess that maybe it can take this form. So we're not sure, but we want to see, can we rewrite this so that it looks like this? And if we do, then what's the amplitude A? What's the frequency beta? And actually, by how much do we have to shift it also? By what value should you add to the radian angle here in order to get the correct thing? Well, one thing you can observe just from this thing that we're playing with is the frequency never changes as I change C1 and C2, actually. Only the amplitude and shift. The frequency remains the same, right? Like I never horizontally squash or stretch what I'm looking at, right? And in fact, let me put 2 pi here for the frequency on both of these. And let's look at what we get. Let's make the plot range. Let's make the plot range 2, 0 to 2. So, what would you measure just from staring at this? What would you measure is the frequency? So, there, I've tuned it so that it sort of looks like it's starting to do something here at 0. So it goes down, up, down. Okay, that was a cycle. Down, up, down. That was a cycle. This distance from here to here is 2. So it looks like the period here is 2. And as I move this around, the period remains 2. The periods of these individual functions, sine 2 pi t, I'm sorry, not the period is 2. In the span of 2 units of time, we do 2 cycles, so the period is 1. So the period is the time distance from here to there. These individual functions have period 1. Right, sine 2 pi t and cosine 2 pi t, they have period 1. And we're seeing that if we take any linear combination of them, the period remains the same. It's always 1. Also, the frequency is remaining the same. So I actually expect that I'm just going to get, for the frequency, I'm just going to get omega for the angular frequency. So I think it should be possible to write it this way. And if you found that argument using the graph in Mathematica unconvincing, good. Let it be unconvincing, because we're actually just going to derive what we can out of here. If we can show that this thing can be written in a certain form like this, then we win. So you don't need to be necessarily convinced of my justification for guessing this form. I can make the guess and then just show that it works. Okay, so if we're going to have this equal this, so one way to try to get this to look like something with a sine plus something with a cosine is to use the sum of angles law for cosine. So this is a times, and then cosine of something plus something. So basically what I'm going to use is this idea that cosine of a plus b is cosine a cosine b minus sine a sine b. So this is cosine, let me write it in a different order, cosine delta cosine omega t minus sine delta sine omega t, like that. And then the question is, can I get C1? So I mean, you see this term cosine omega t here and here, right? And you see sine omega t here and here, right? Then the question becomes, can I get C1 to be a times cosine delta, and also get C2 to be a times negative sine delta? So now I've got this system of equations that if I can solve, then that will be victory. I will find a way to figure out the amplitude and the phase shift for this thing. So here's my system of equations. A cosine delta is C1, and minus a sine delta is C2. Okay, so how do I solve this system of equations? This is not simple. I mean, it's just algebra, but it's not simple. So one thing you can do to try to eliminate the delta is take the sum of the squares of both equations. So C1 squared plus C2 squared is the sum is the right side of this squared plus the right side of this squared. So that should equal a squared cosine squared delta plus negative a squared, which is a squared, sine squared delta. So that's a squared times cosine squared delta plus sine squared delta, which is a squared. So then a is the square root of C1 squared plus C2 squared. That's neat. So we just found the amplitude. If this works in the end, if this system has a solution, then we found what the amplitude would be. And spoiler, the system does end up having a solution. And for example, this one, the amplitude should be the square root of 5 squared plus 7 over root 3 squared. So let's see if that's correct. Let me plot a flat line at that value, and let's see if that flat line really rides the top of the waves. So I'll plot a constant function square root 5 squared plus this thing squared. And let's see. That's perfect. So apparently whatever this number is, that is the amplitude of this thing here. Great. So we answered one of our questions. Given this thing, the amplitude is this. Okay, what about the phase shift? So the delta. This delta is called a phase shift. So what about that? Well, one nice thing you can do to get rid of A is divide one equation by another. So if you divide one equation by another, you get, let's do the second equation divided by the first equation. You get minus sine delta over cosine delta, and the a's cancel, equals C2 over C1. Or in other words, tan delta, move the minus sign to the other side, is minus C2 over C1. So that gives you a way of computing that phase shift delta. So delta must be the arctangent of minus C2 over C1. And that pretty much works. Well, let's observe whether or not it works. Let's try it out. So back here, let's see. Instead of plotting this constant function, let me plot this times cosine of omega t. Oops. Cosine omega t, and then let me add delta. Like this. And of course it's not going to plot anything because I haven't said what delta is, but let me define delta here. So I think delta should be the arctan of this thing divided. Wait, that one is C2, right? C2 stands for whatever is the coefficient in front of the sign. Yes, this one is C2. And then divided by C1, that's 5. So let me try that. Ouch, that is wrong. So I wasn't sure if that would come out wrong, but there was a 50% chance it would come out wrong. So to be clear, what I was expecting is that when it plots the orange line, that it's right on top of the blue line. So my goal is to get this thing to be exactly the same as this thing. But it seems to be shifted incorrectly. So yeah, so what do we do? What's going on? So let's check whether we actually solved this equation with our A and delta. Okay, so let me copy my delta here. Copy the delta over to a new cell down here. And then let me define A. A was, let me just copy it over. It was here. So there's A and delta. And if I do A cosine delta versus minus A sine delta, I should get C1 or I should get C2. So I don't know why I said versus, just if I do both of those. So let's try it. A cosine delta, that's 5. That's good. That is C1. That's this one, the 5 there. A sine delta, 7 over root 3. Is that correct? That actually sounds correct. No, sorry, it's not correct. The left-hand side here is negative A sine delta. And so I get negative 7 over root 3. So I'm off by a minus sign, it appears. Oh, I see my mistake. The formula was tangent delta is negative C2 over C1. What I wrote down here, delta is negative arctan C2 over C1. So I should have done it like this from the very start. Ah, there we go. Now the orange line is on top of the blue line. So now these really are equal. Yeah. Okay. Okay, so let's go back here to our original function here. When we solved this initial value problem, we got this thing. And now we have a much nicer way of describing what it looks like. So we can answer this question. What does this look like? We'll write it using that other form. So we can write it as e to the minus t over 2 times a, let's call it, and then we'll say what a is in a moment, times the cosine of square root 3 over 2t plus delta, where a is the square root of 5 squared plus 7 over root 3 squared, and delta is the arctan of negative 7 over root 3 over 5, whatever we got. So this is what it is, and now you can much more easily say what it looks like. You've got this sinusoidal function with root 3 over 2 as its angular frequency, so you could figure out the expected kind of period from that. And here's the amplitude. It is an exponentially decaying amplitude. It's just that it's not scaled by 5 or 7 over root 3, it's scaled by whatever this value here is. So when you do this, when you rewrite something from this form into this form, this is called phase amplitude form.